Hello everyone, we're ready to start. Today the topic is the application layer. The application layer is the perhaps most interesting part of the internet. That's the distributed application themselves. And it includes also things that are put typically in the application layer that we will discuss here. You did several application layers in the socket programming labs. I mean, each of the programs you did was a small application layer. In this module, we will not focus on how some large and important applications are built or designed or run. We will focus instead on generic issues, the ones that are relevant to the protocol world. Still a few words about perhaps the most widespread application, which is the world of web servers. HTTP has evolved from version 1, roughly speaking, 1.1 to version 2, where the main difference is that HTTP typically uses TCP. You can run HTTP and UDP, but most of the time it's not done. So HTTP typically uses TCP, and the most recent version of HTTP allows to use the same connection for several objects, the same TCP connections, whereas previous version of TCP was taking a radically different approach, was using one TCP connection per object. That is where the evolution led. So let's reason about what that means. For example, consider the following scenario. A server sends me a web page, which, if you have a modern web page, will typically have a large number of embedded objects, images, banners, scripts, perhaps also even some video files. And your browser will integrate all of this and render properly the web page. If we use HTTP2 over a single TCP connection, the browser will typically do things as fast as possible. This is why sometimes you see that the page being displayed varies a bit as your browser is able to download all the elements. Now assume one packet of the first object is lost. Of course, since we use TCP, TCP will be retransmitted. But what do you think is a plausible scenario for what happens next? So this is a poll. We will open a polling window in which you can give your answer. I will close the poll in a few seconds. I close it now. And surprisingly, the majority says A, but this is not the correct answer. It's not the correct answer because if we use HTTP2, we use one single TCP connections. So if I go back to the image of the previous thing here, HTTP2 allows to do things in parallel from the viewpoint of the programmer when you program things in the script on the server side, for example. However, it uses a single TCP connection. So what happens with TCP is that if TCP provides a streaming service, so if one part of an object is lost, then, for example, if the first packet of the red object is lost, then the TCP connection will not deliver any of the things that come after. So what will happen is that the second object is simply not visible to your web browser because it is still in the socket buffer waiting for the loss of the previous packet to be repaired. So the correct answer is B. The second object must wait for the first object to be completely received. That's a problem of TCP that we will discuss in a few minutes, is addressed by alternatives to TCP, which are QUIC, for example. A small other quiz to just clarify things. Here's an example of FTP. FTP is something a bit obsoleted. We typically use HTTP to do uploads, but there are still systems that use FTP or secure versions of it, SFTP. Here is how the traditional FTP system works. FTP is a file transfer protocol. And the goal is to be able to move files from one machine to another. The traditional way of using it is to open a TCP connection from the FTP client to the FTP server. And this first connection is the one over which you send commands to the FTP server. So with FTP, you not only transfer files like you do with HTTP, but in addition, you open a shell. You open an interactive command, a window into which you can send commands. So this is done over a first connection. And the traditional FTP mode, over this connection, you say, for example, I want to upload or download a file. And when you do this, you give to the server the port number over which you would like the file to be downloaded to. And then it's the server that opens the TCP connection to you. This is a traditional FTP active mode here. This doesn't work with most firewalls because that means there's a TCP connection opening that comes from the outside to you. So many firewalls will kill this packet unless this port is declared in your firewall. So this is why there's a version, an alternative version of it, which is called FTP passive mode that replaces it. If we consider the FTP active modes and we look at all the different ports that are port 20, 21, and the port 1, 2, 3, 4, 6 here. So I focus on those three ports only, 21, 20, and 1, 2, 3, 4, 6. Which of those ports are TCP server ports? I close the poll in a few seconds. And the majority says D. We're unlucky today with the majority votes. The correct answer is not D here, but is F. Why is that? Well, the definition of a TCP server port is a port on which we are waiting for things to come. So it's when we do first a listen socket statement, we listen on the port, and this port, oops, thank you for sharing the results, Aladdin. Then this port is the port that is associated with waiting for a connection request to come, a SYN packet to come. So the 21 port is a server port. It's a well-known port of FTP, and any client can send to this. Of course, 1, 2, 3, 4, 5 is an ephemeral port, allocated, a temporary port, allocated to you by the operating system. But here in the FTP active mode, we see that it is the FTP server that has to open a connection to the FTP client. So 1, 2, 3, 4, 6 is in reality a server port, and 20 is a client port. So 20 is a well-known reserved port number to be used by an FTP server, but it's not a TCP server port. Here you don't do a listen on this port. If you look at the code that does this, you do a listen here, and here you will do a connect. So you open another socket on port 20 that is used only as if it would be a client here. So the correct answer is this one. 21 and 1, 2, 3, 4, 6 are server ports, 20 is not here. Of course, this is a bit weird, and this is why most applications today would use FTP passive mode, and in this case 1515 is indeed a server port, a temporary one that's allocated by the FTP server, and now the server ports are on the FTP server side, as everybody would like things to be. So this is to illustrate what really server and client means in the context of an interaction in the internet. And we see that it's not what is typically called the FTP server that does it, or the whatever server. And in particular, we have lots of peer-to-peer applications that combine all those different elements. Voila, this was for our first discussions. A few minutes ago, I mentioned we saw in the quiz that TCP with HTTP2 has a drawback in terms of performance. So this drawback is exactly one of the two motivations of QUIC. So QUIC is formally an application layer framework that replaces TCP, is meant to replace TCP. So we could teach QUIC in the transport module, but the transport module is already very big. Learning how TCP works, we have to do it in two parts. TCP per se, then the congestion control module. So doing QUIC in addition would mean a lot. So I prefer to do it in three parts. The motivation, another motivation of QUIC is also to integrate the secure transport. If we do a secure transport, the way we did it in the lab, in lab 3, we use HTTP over TLS. So we insert an application layer framework, which is really a security framework that upgrades the TCP sockets to transform them into secure sockets here. And when we do this, we see that we have at least 2 RTTs before we can transmit a single piece of information, which is what we do most of the time today when we go over the internet. Hopefully we use secure connections. We don't go to a random unsecure internet site, because this is very risky. So before we go anywhere, we use TLS. We have discussed that in the transport module. That involves in particular verifying a certificate. So we are certain that we're opening a connection to a site that corresponds to the identity that is displayed here. Before that, we need to open a TCP connection. Once the TCP connection is open, we need to open the cryptographic channel, which requires at least 2 round trip times here. So that is another latency problem of the current way of doing HTTP over TCP. So the first element of latency is if a packet is lost, then everything is blocked until this packet is, this loss is repaired. The other one is this double handshake. QUIC is a solution to avoid this. So it avoids the latency and the head of the line blocking of TLS over TCP. Now we could say the standard way of doing it would have been to modify TCP, to do something that would be a modification of TCP that integrates TLS. But for practical reasons, which are bad reasons, but that's the way the world is, if we do any modification to TCP, then most firewalls will kill the traffic here. So the reality today is that we have firewalls, and the most important firewall is probably your ADSL modem at home that interfaces between the public internet service provider and your private network and does things like NAT, and it does NAT, but also verifies and filters everything that is not appropriate. Such firewall functions are very, of course, they need to be updated. If you have a new version of something, then the firewalls that are deployed will not be compatible with that, and the traffic will not work. So the firewalls are fossilizing the internet. They force the internet to continue being compatible with whatever the firewalls do. But of course, this is completely ridiculous, because what a firewall does typically, it allows UDP traffic to go unmodified. So the quick solution is to say, well, we will do everything on top of UDP, which means we put the port numbers in UDP, and all the things that TCP does, like sequence number, acknowledgement, etc., we will put them in a quick header that comes on top of UDP. So that's what the status of affairs leads us to today. We could have done that 30 or 40 years ago. TCP could have been done on top of UDP. It could have been a separation. Since the UDP header is very small, we could view TCP as an additional layer that's added on top of UDP. That's not the way it is done. That's not the way it came historically, but this is the way new versions of transport are coming today. So that's the first thing that's to say about QUIC. The second thing is that QUIC mandates TLS. So QUIC will not do like with TCP. First, we open a TCP connection, then we add a cryptographic channel on top of it. Here it's the other way around. Before doing anything, we first establish a cryptographic association between the two ends, and only once the cryptographic association is established, we start transferring data. So we do things the other way around, and that is a healthy thing to do today because we want every connection to be secure here. So that means with QUIC, data is always secure. You cannot go to a website that would not use TLS. The second optimization, well, the first optimization that QUIC does is that it does everything in one step because it integrates TCP, or the functions of TCP and the functions of TLS. Instead of first opening a TCP connection, then exchanging the cryptographic material, we can do everything in one shot because we design it from scratch. So the first property, which is very important in terms of latency, is that QUIC establishes the TLS session first, does that over UDP without any TCP connection being done first. So the visible benefit will be 1 round trip time instead of 2 in the best case if we use TLS 1.3. The second thing that QUIC does is to solve the problem we saw in the quiz a few minutes ago. QUIC allows multiple streams. So QUIC does not depart from the model of TCP, which is stream-oriented. So QUIC continues to be stream-oriented, but it allows to have multiple streams, and the streams are very lightweight. There is no overhead in creating or deleting deleting, you can send a reset, which is an overhead packet, but there is no overhead in creating a stream. You simply send data by putting a stream identifier. A new stream identifier would automatically mean a new stream is connected. So every stream in at least the current version of QUIC is reliable. There are discussions of making unreliable streams as well, but today every stream is like one TCP connection. So data of the stream is delivered in sequence, and if one packet of this stream is lost, it will be retransmitted, and the subsequent data cannot be delivered until the loss is repaired. But since we have multiple streams, we expect that HTTP over QUIC, which is HTTP number 3, so the HTTP 3 version means the version of HTTP that runs over QUIC, and then it typically uses one stream per object. Stream 0, the default stream, is used for setting up the QUIC connection, and in particular to set up the secure transport association. Another difference is we have multiple streams, but we don't have multiple packets or multiple headers. One QUIC packet has a sequence number. So we see one QUIC packet has a sequence number, and a QUIC packet can contain data of multiple streams. Most of the time that's not the case because a packet is limited in size. So if you transfer a video object, you will not have space for anything else in a packet. But you can, if objects are small, in particular if there's a small update to the TLS channel that can be carried in the same packet as stream data. And the packet number is not per stream. So QUIC sends a packet. If a packet is lost, this packet will be retransmitted. Exactly this packet will be retransmitted. And the sequence number of a packet is retransmit is not like a TCP sequence number. A retransmitted packet will have a different number, which from a cryptographic view and security viewpoint is better because that defeats replay attacks here. Other than that, QUIC is doing minimal changes. So everything in QUIC is otherwise similar to everything we've seen. The retransmission is exactly the same as TCP. There are several versions of QUIC. QUIC was originally developed by Google and is being standardized, and there's a fork between the Google version and the standard version, so there are variants, but essentially the take-home message is that QUIC does exactly the state-of-the-art of TCP, so it uses all the best known algorithms that we saw in the section on bells and whistles and TCP, like fast retransmit, tail loss probes, acknowledgements that try to be based on the reordering time and not just the detection of a loss, etc. Also, another benefit compared to improvement compared to TCP is that the number of ACK blocks is very large compared to TCP, because in TCP, this was in the TCP header where we didn't want to inflate it too much. Here, everything is more flexible, so we're able to detect exactly what is lost here. Flow control is both per stream and per connection. So flow control, remember, is the function that allows a receiver to express to the source at which speed it should send. So it says this is using a window. Here it's similar, but the terminology is different, it uses an explicit offset. And it's both per stream and per connection. So the receiver may have all the streams on one machine, in which case it makes sense to be per connection, but there may be multiple processing units on a receiver that handle the different streams. For example, you may use a different core for the video than for the JavaScript, and so you may flow control differently those different streams here. So this is possible in QUIC. Congestion control is per connection, not per stream, which makes sense because per connection control is about controlling the volume of traffic that goes into the internet, whether it's 20 streams or one stream, as long as it goes from the same source machine to the same destination machine, it is the same flow for congestion control. So it is done per connection, and it is in the standard version exactly the same as TCP Reno, and in the Google version, the original version, it was cubic. Well, obviously the difference is not large anyhow. So this is exactly the same function. So we have an example of a UDP application. If we use QUIC, we use a UDP. We are using a UDP application, and that uses exactly TCP algorithm with the controlling the window which exists at the level of the connection here. As I said, unreliable streams are also foreseen, but this is for future story. Of course, as you can imagine, all of this makes QUIC considerably more complicated than TCP. So there is no QUIC socket. That's the bad news. QUIC is used typically by a library. So you need to use a more complex library in which you do you use all those functions, setting up the stream, etc., which is considerably more complicated than using sockets. So the major thrust behind QUIC was to reduce the latency for short HTTP interactions, which is one of the major problems of companies like Google. If you go to a Google site, you would like things to be set up very quickly. And with QUIC, this is what is achieved. But of course, it allows a number of other improvements. Here's, for example, what of your predecessors, master students at EPFL did with QUIC. In the context of a smart grid, you will have a sensor, PMU, that sends one measurement every 20 milliseconds. Now, we would like those measurements to be received reliably, so we can use TCP, or if we use UDP, then it's a pain because we have to do things. But using TCP is also not optimal because we have head-of-the-line blocking. If a measurement is lost, then an intelligent use of reliability would require that we retransmit perhaps not the measurement that was lost, but the newer measurement if a newer one exists. So if you detect the loss 1 millisecond after generating this one, then you would retransmit this measurement. But if the loss detection takes more than 20 milliseconds, there is no point repairing the loss. It's better to deliver the next one. But with TCP, you will not be able to do that. With TCP, you will repair the loss, which may delay a new measurement. So in some sense here, the head-of-the-line blocking with TCP is counterproductive. It's not adapted at all to that time of application. But with QUIC, you can do that. So the solution done by your predecessor, Wayu, was to, for every new measurement, to create a new stream. So that's illustrating the facility we have in QUIC to open streams very easily. And as soon as a new measurement comes, you kill the stream if it's still working and if it's not acknowledged. So with that, you will have both the best of both worlds. If a message is lost and you can repair it very quickly, you will repair it. But if you can't, you will not have head-of-the-line blocking. You will send a new message over a new stream, which will not block the previous one. So that's an example of the modern transport environment. And in the future, we expect that there would be more and more of these variants of QUIC that will show up here. Time for a little quiz. Assume you're using an app and you use the YouTube app, which has a Google app. All Google apps try to use QUIC. Will the app be able to use QUIC? I close the poll in a few seconds. And the overwhelming majority says C, which is correct. Because QUIC is over UDP and all the cryptography and TLS is over UDP, the UDP port numbers are not encrypted, so they will be visible. So the NAT, which works well with UDP as well as TCP, will do its work as usual. So it will work. As you can imagine, of course, Google would not have started a new app, a new framework that doesn't work over NAT because everybody is using a NAT. Voila, that's for QUIC. Another application, in some sense, formally, is the domain name system. It's not really an application, it's part of the infrastructure, but it's in the application layer. So let's say a few words about DNS. We've encountered it many times, so some of it is familiar. We know that the DNS was invented essentially to hide IP addresses and transform them into names. Originally, it was because at the beginning of the internet, when there was not Google search or Alta Vista search before that, we really had to know the name of a service in order to go to that service. So you would type in ftp.epfl.ch to go to your FTP server, for example. And there was no easy mechanism to find that. So it was a convenience to have names instead of obscure IP addresses here. Now, with the advent of search engines, we could say we don't need them at all. We could well use the IP address. The search engine could return the IP address followed by the rest of the URL, which could be done. But as we will see, the DNS still serves a number of very useful roles today and is really at the heart of the internet and is used extensively by all online services, not just to give a user-friendly name, but also for other things as well. So a few words how the DNS works. Originally, the DNS, first defines what are the valid names, and names are hierarchically organized. At the top of the domain, there are three or two letters. There used to be 2 letters, which are all for countries, or 3 letters that were the non-country original names at the beginning. So .com, .edu for educational entities, .gov for the government, .mil for the military, .net for the internet itself, .org for non-profit organizations, and 2-letter acronyms for countries here. Now this has been open and any name is possible. If you put enough money on the table, you can create your own top-level name. Then once somebody has a name, they have to, they own this name and they can sell or give to other people other names inside this domain. And we know, for example, .ch is the domain that belongs to Switzerland, so it has been given to Switzerland, and Switzerland delegates what we call this to a register. And EPFL, for example, can ask to obtain the EPFL.ch name, and you can do your own if you want. Originally, it worked only with English characters. Now you can, there is what is called a Punycode that can be used to translate any other characters into, or a large number of those characters, for example, with umlaut or other such things. How does it work? So the DNS is essentially a big database, but it doesn't work like a database. We will see that it works in a much more lightweight manner. Databases are plagued with performance. You probably all of us did the experience once we have a web development project, we put a database into it, and then it becomes slow because of the database. So DNS did not want to do databases. It does simple lookup into tables, and it works as follows. When you map a name to an address, for example, because you clicked on something in your web browser, your DNS resolver contacts a DNS server. So which DNS server? Well, that's, as we know, has to be given by the configuration of this machine. Typically, the DNS server doesn't know the answer. So let me illustrate here. You go to the DNS server that is serving you. So who serves you? Well, there are public DNS servers that serve everybody, like the Google one, 888, for example. But typically, if you're inside an enterprise, you cannot use those DNS servers, so you will use the DNS server of the enterprise or of the internet service provider who provides service to you. Typically, your DNS server doesn't know the answer because your DNS server knows, for example, in the case of EPFL, it knows only the names that are allocated by EPFL to EPFL. So if you click to a zurich.ibm.com address, for example, you have to ask the Zurich, the DNS server that's responsible for the ibm.com. How do you know which server that is? If you know nothing, your server will go to the root name server. So there are 13 root name servers in the world who know the IP addresses of all the name servers for all the top level domains. And also, in the case of .com, of all the domains such as ibm.com. So the EPFL server will go, if it doesn't know it, will go to the root name server with the same query that was asked by Lisa, and will get a reply, and the reply will not be the answer, but it will be something that helps with the answer, what is called an NS record. NS stands for name server. It will be the IP address of name server. The names also, but the names are useless here because we're not able to resolve names of IBM. So it will give IP addresses of machines that are DNS servers for the domain ibm.com here. Once your server gets that, it will ask, it knows now whom to ask, it will ask and get the answer here. While doing that, your DNS server is operating in what is called recursive mode. Recursive means that with a single call to the server, we get the job done. And it's recursively done because we get something that needs to call the DNS again. DNS servers that serves clients typically accept to be recursive. DNS servers that serve other DNS servers typically do not accept to be recursive. Why is that? Well, because being recursive means you keep state information. This server needs to remember the request sent here and work until the request is resolved here. So if you are a root name server that is exposed and has to be extremely high performance, then you don't want to do this. So this is one of the options you give. RD means whether recursivity is desired or not here. Typically from a client to your home DNS server, you ask for recursivity, but when you talk to the outside, you don't here. Here I've shown an example of record. I've mentioned the NS records. There's a large number of possible records in the DNS, but the most used ones are the A and quadruple A. The A means IPv4 address and quadruple A means IPv6 address. So for example, here I'm using the program called DIG, which is a very useful program you find on all operating systems. I use DIG to call for an A record for this name here, which is one server of ePFL, and I see the answer I obtained. The answer contains the name I was asking for. Then a C name is a canonical name. It's another type of record. That's something that maps a name to a name. Typically, when you have services like lca.epfl.ch, this is something that is quite generic that you can map to different machines. Here it happens that it runs on this machine, LCA1 SRV2. Perhaps tomorrow it will run on another machine. So this is an indirection mechanism that is very useful and is used a lot in the internet. Of course, if I get another name, it's not useful. So this DNS server was smart enough to return not just the canonical name, but also the IP address, which is what I was asking for. Similarly, if I ask for a quadruple A, that means I'm asking for an IPv6 address. So we see that when we go to the DNS, we have to explicitly say whether we want IPv4 or IPv6 addresses. In the example I showed before, I was assuming that the DNS server of ePFL doesn't know the IP address of a DNS server that serves the IBM.com domain. Of course, most of the time, it will not happen in this way because we are able to cache. Caching is an old trick we see everywhere in this course. And this is where the DNS differs from a database system. So how the DNS works is the DNS will remember things it has already resolved for some time. How much time is dictated by whoever puts the records. For example, the DNS server of IBM has a cache of 2 hours, has a TTL of 2 hours, which means that when they put in the root name server their IP address, here it is valid for 2 hours. ePFL names are valid for 2 days, much longer time. So whenever a DNS server or even a DNS client gets an answer from another DNS server, it will keep it in its cache for the duration that it has obtained from the DNS server here. And why do we have a time to live that is dynamic? Well, it is because when the time to live expires, the DNS server that has cached it will forget about the entry which is in the cache. So this is the mechanism by which we can have dynamic entries. If you want to have a dynamic entries, you set up with very small TTL, a few seconds. If you want static entries, you put longer TTL because you don't expect them to be changed very often here. We see here, for example, that the answer that is given back to Bart has a value which is a bit less than the original value because it's a value that is obtained from the cache. Lisa clicks, asks to go to this site. The answer is stored in the ePFL server, but as time passes, the value of the TTL decreases here. And so when BART gets the answer, if BART wants to cache it, it knows it will need to cache it for a shorter amount of time. So that if sometime in the future, watson.ibm.com changes the IP address of the service that is given here, then 2 hours after the change, the servers here will be able to recognize and stop using the value in the cache. We have seen also reverse DNS lookup. A reverse query is something that is done, for example, by the traceroute program. When we use traceroute, for example, for this thing here, we know how traceroute works. I recall how it does. It sends a sequence of packets with increasing TTL, IP TTL. And the first packet expires at the first hop, and the first hop hopefully sends an error message. And by analyzing the error message, we have the IP address of the first hop, and the DNS name of the first hop is obtained by the traceroute program that does a reverse DNS lookup that asks the DNS who has this IP address here, which is not the normal intended use of DNS, but is one accessory one that is supported here. How do you think that the reverse DNS works? Little quiz. I'll close the poll in a few seconds. And the majority says B, which in some sense is the correct answer, with a little variation. The DNS server will not search its database for a reverse record, which is what you would do in a database. The beauty of databases is that once you have written your records, you can search for any criterion. So you could search your DNS file and say, give me all the names that correspond to this IP address. That would be a reverse search. But we don't do that in the DNS. Typically, you can do it if you write a non-standard DNS server, but typically we don't do that for performance reasons. Searching backwards takes at least linear time. So what is done in CERT is we pre-process by writing reverse records. So for every IP address, you can write, if you want, in your DNS server, a record that corresponds to this IP address. And the record type is PTR. That means that if I, for example, go to my preferred DNS server and I ask, what is the IP address, what is the name that corresponds to 128.178.15.8, I will translate that into a name. So there is a high-level domain, IN address ARPA, which stands for IPv4 addresses here. And I will ask for a PTR record here. And what the DNS server will do is look for a record by looking directly for this one. You will not do a reverse search. Of course, it's up to whoever runs the DNS zones, whoever owns this IP address, to do it correctly here. So if EPFL injected in its DNS zone incorrect records, the inverse mapping will be incorrect here. Here, it's not the case. I obtained from the DNS server this name here. If I now try to find its IP address, I find the same. But there is no guarantee that it will be the same because it's not a reverse search. It's really searching a pre-processed something else. And this is exploited. For example, there are wrong records introduced here. When you look for things, you will have completely wrong names that don't correspond to anything. Okay, let's perhaps time to do a break. So it's 1 o'clock. Let's do a 15-minute break and continue our discussion of DNS after the break.